Hi there, I'm Hugo, one of the authors on a new paper looking at behavior change in computational models. So often in our computational models of various phenomena, we'd like to model individuals' behavior change in response to some stimuli. So for example, in a model of a disease outbreak, we might want to model how individuals change in their lockdown adherence rates over time. Some models do include submodels that account for this. However, they're often quite simplistic, and importantly, they're not calibrated to real-world data. So in this paper, we ask and answer the question, can we develop a simple model that is fully identifiable from real-world data? So to introduce the data a little bit before I talk about the model, we're using reversal learning experiments where the subjects choose between two options and reward associations switch at a reversal point. This setup captures learning through rewards and behavioral persistence after conditions change, and importantly, we have real-world data from experiments on guppies by Boussard and colleagues. So now to introduce our model, it's quite simple. It just has two parameters, memory decay or tau, which determines how quickly past experiences fade, and decision certainty, k, that reflects how confidently individuals act on information. The subject, or the individual, just keeps track of a single utility value that affects its chance of choosing a particular option. So here's a sample run of our model where we show the learning process. The individual initially learns to choose A almost all of the time, and then must relearn to choose action B after the reward reversal at time step 30. In the paper, we also show that we can effectively identify the two parameters using approximate Bayesian computation, with clear posterior distributions concentrating around specific values that you can see in subfigure B. This confirms that our model is both mechanistically adequate and statistically tractable. For long-term dynamics with multiple reversals, we add a third parameter, theta, that captures how quickly certainty decays over repeated changes, enabling us to simulate the declining success rates observed over multiple reversals in the original experiments on the guppies. So in summary, we've developed a simple, identifiable model of behavior change that captures adaptation processes and can be extended to complex scenarios. Future work could expand this to non-binary decision problems where we have more than two actions to choose, as well as explore individual level calibration techniques. Thanks for listening, and I hope you enjoy reading our work. Thanks.